I'm now recording on my end. So, welcome to the 532 Signals and Systems 1 final exam tutorial for fall 2022. So, like I was just saying, we're going to be going over the practice midterm that was posted. I think it was the 2017 one, if I'm not mistaken. The 2017 one, which our professor posted. Before we get started, as always, this is being recorded. It will be posted on my YouTube channel, which is just my name. Just posted on YouTube, which is just my name. So let's start with that, Adam Sava. Then my notes for this course you can pick up as always on my website. So notes are available at www.tutor.ca/notes, and there's notes for all my courses there. Well, yeah, I try to keep them up as good as possible, but sometimes I don't. So but for this course they are up to date. There wasn't that much to say in the Laplace section, to be honest. It was kind of just doing the Laplace transform is the most difficult part. I might add a little bit from here to the exam, so keep an eye out. And then the PDF for this video will be in the description of the video. The PDF for what I'm writing here will be in the description of the video, if you're interested in that. Yeah, so let's get started, I guess. Let's see. Everybody can see my screen. Confirm? Yes? Everybody can see what I've written here? I don't want to start writing and then nobody, thank you very much for yeses. And let me just make sure this is connected properly. Okay, so let us begin the journey. So the first question gives us a pole zero diagram. So we didn't really talk about pole zero diagrams in lecture, if I remember correctly, but they're not that complicated. So basically, let's just read it. Let S be a linear time invariant continuous system, which is the systems that we deal with in this course. Oh, by the way, I'm going to have the formula sheet here. I have it printed, so I'm not going to pull it up on the screen. So I'd recommend people have the formulas, have the formula sheet in another tab or something like that, so you can see. I don't like flipping back and forth to the formula. So it's a causal system with a transfer function h of s. The pole zero diagram of h of s is shown in the figure. So the pole zero diagram, all you really need to know about h of s is where the poles are and where the zeros are. So these are the poles, and these are the zeros. Those are zeros, those are poles. I will be posting this recording to my YouTube channel, yes, that's all. So the idea here is this is all we need to know. We can just the system is defined by this, basically. So the first actual question is determine if the system is Bibo, stable, and causal, determine h of s and its region of convergence. So what are these two things? If it's Bibo stable, that means the region of convergence has to include the imaginary axis, right? That's what that means. So if it's Bibo stable, the imaginary axis has to be included there. Our region of convergence is always defined by the poles, always. It's either to the left or to the right of the poles, right? Since it's causal, that means it's to the right. Causal means that means to the right. So basically, our region of convergence will be, this way intersected with this way. So basically that means this is our region of convergence. This is our region of convergence. Right, passes, because it's to the right of -3, but also to the right of -1. So both of those would be, the intersection of those two would be. Okay, so that's our region of convergence. It doesn't particularly matter. Well, it kind of matters, but it doesn't really matter when we're just trying to determine h of s. So to determine h of s, right? Remember, h of s is a polynomial. Well, it's like a rational function, two polynomials, a polynomial on the top and a polynomial on the bottom. E of s over q of s. And so p of s is defined by these zeros, right? The zeros are going to be it is 2j and -2j, so it's going to be s minus 2j. Now I'm going to have to be really careful with s's and 5s. So if I may get confused with s's and 5s. That's what pretty much what I'm trying to say here. So I'm going to try to write 5s like that, but I end up like that. Yeah, so I could certainly write like a little, little guy like that. That's not a cursive S. I know I'm just being a little extra. And then, but sometimes if I have to have an S and a 5, I write S's like that. Is the green highlighted from -1 onwards? Yeah, from -1 onwards. I might write S's like this. Anyways, just warning you. Keep an eye out. So, and this is S plus 2j. So that's the numerator, right? Because it has to have those two zeros that were given to it. And then the denominator is just going to be S plus 3, S plus 1. What is the 2j's versus? Well, the 2j's are just are these values here, the two zeros, right? So yeah, it represents where the transfer function is 0. So that means the output of the whole system is going to be 0. So yeah, okay. So there's our transfer function. Technically, there could be a k here, right? There could be a constant scalar, but we're just going to, for simplicity, say that's it. And there we go. Because for the k there would just have that. So there we go. K would be some sort of gain. Yes. So it wouldn't change the form, right? It wouldn't change the form of the actual h of s. So there we go. We used all the facts. We used that it's Bibo stable, which means it has to be right-sided. Causal, which means it has to be right-sided. And well, sorry. So Bibo stable doesn't mean it has to be right-sided. Sorry. Bibo stable means it has to have the y-axis, the imaginary axis, and causal means it has to be right-sided. So there we go. And we got this function. So great. So that's that information. Oh, I guess then, and this region of convergence. Sorry, just to be clear. And the region of convergence is sigma greater than -1. So there we go. That's part A. Now, what would the region of convergence be if it wasn't Bibo stable? Then yeah, if it wasn't Bibo stable, that means you can't include this. So that means like our region of convergence would have to be like that, or it'd have to be like, I guess it'd be that. No, but then it would be causal.
Then it would be causal. Everything except the imaginary axis?
Possibly. It could be the same kind of form, but just with the exact exception of that. Yeah, it could be that. I don't know why it would be that, but it could. Like that would match these two things. I've never seen that before, but that would match these two conditions. So it certainly would not include the imaginary axis if it was not Bibo stable. Okay, let's keep moving. So from the information given, can you determine the asymptotic stability of the system S? If it's possible, then determine the asymptotic stability of system S. If it's not, explain why. So we can determine the asymptotic stability. And I'll show you a little textbook blurb that tells us why. So page 372 on the textbook. This is what we read. I just control F the asymptotic. Yeah, it's been chapter 4. I found this. Yeah, sigma is the real part of the, right? This is the sigma. This is the sigma omega plane here, right? Page number is 372 of the textbook. So remember, like I said, it's P of S over Q of S. So if P and Q do not have common factors, then the denominator H of S is identical to Q of S. Like, yeah, which is right. And the characteristic polynomial of the system. So in this case, so this is just the characteristic polynomial of the system. So because of that fact, we can basically treat the poles just like we treated the solutions to the differential equation, like the characteristic values of the differential equation when we did in chapter 2. Remember, in chapter 2, you have these conditions for asymptotic stability. Maybe I have it in my notes somewhere. Open my notes. And so we can just treat the poles as the same thing, basically. That's the conclusion here, is that we can treat the poles under the same conditions to determine asymptotic stability. Of course, Notion has to do something right now while I'm trying to open my notes, so let it do that. So what are the poles? The poles are -3 and -1, right? So what are the conditions? An LTI system is asymptotically stable if and only if the poles of its transfer function, H of S, are in the left-hand plane. Great. That is what we have. therefore asymptotically stable. And that's that. Not this course. So let me just find, so these are my notes here. Let me find where I specifically said, where is it? Internal asymptotic stability. Do I have a chart? I think I have a chart for that, don't I? No, I don't have a chart for it. I think in the textbook there's something. Oh no, this is asymptotic stability. Is this stability? Yeah. So basically, yeah, this is kind of it, right? So we got to kind of think back to this here, right? To recap the rules. If both zeros are in the left-hand plane, right, then it's going to decay, right? So it's stable. If they're both in the right-hand plane, or if any are in the right-hand plane, right, it's going to undecay. So it's going to be asymptotically unstable. Then you have these special cases, which are annoying, right? So if you have unique roots on the imaginary axis, that's fine. If you have repeated roots on the imaginary axis, that's not fine, right? Otherwise, yeah, that's basically it. So this particular question is asymptotically. And I would just explain that. So basically, in words, I would say determined it. I would say, treat the denominator of the transfer function as the characteristic polynomial of the system, because it is, apparently. I can't prove that, but apparently it is, according to this textbook. And there we go. And then you can just use the same rules that we talked about from that section, chapter 2, onto here. Poles on the imaginary axis imply that they are purely complex, right? That is correct. They're purely imaginary. I thought if it's on the y-axis, it was marginally stable and unstable. Marginally still means system is unstable. Yeah, maybe. I don't particularly recall. Let's see what I have here. Do I have here? So marginally stable if simple roots, unstable if multiple roots. So simple roots means unique. So yeah, so if it's on the axis, and they're unique, then it's marginally stable. Okay. So there's that. There's that question. Next is we want to make basically just make direct form 1, direct form 2 of the system. Sketch block diagrams that depict direct form 1, direct form 2. I have a heated blanket on me. It's a little bit too warm. Turn it down. So we have direct form 1, so let's start with that. Direct form 1. So before we even do any of that, I got to look at the transfer function a little bit. I got to look at our transfer function. So that's h of s equals, and it was s minus 2j, s plus 2j, all over s plus 3, s plus 1. So I got to get this into like a standard form, basically, like for all the polynomials. So this is going to be s. The top is going to be s squared plus 4, yeah. And the bottom is going to be s squared plus 4s plus 3. Great. That's important. Now, what we got to do is we got to divide everything, right? You got to divide everything by s squared. Yeah, zeros have nothing to do with asymptotic stability. We can just ignore them. Yeah, according to this, yes. Zeros have nothing to do. Actually, it even says there, right there. The location of the zeros of h of s have no role in determining the system stability. So I'm going to divide everything by h. Sorry, and before I even do that, actually, I'm going to make sure this is a 1 here. It is a 1 here. So I don't have to do anything, but I'm just going to mention that because if it's not a 1, you have to divide out. So, okay, so now I'm going to divide everything by 1 over s squared. Multiply everything by 1 over s squared. It's going to be 1 plus 4 over s squared over. You can think of it like there's a 0 over s here if you'd like. 0 over s. Okay? And it's going to be 1 plus 4 over s plus 3 over s squared. So basically, we have a bunch of values, right? B naught, B1, B2, A naught, which will always be 1, A1, 2. So we can just build this now. So direct form 1, this is how I remember it. Direct form 2 is the better one. So you have all the integrators in the middle. Direct form 2 is the worst one. So you have the integrators on the outside. Because direct form 2 you can like combine, right? So direct form 1, the integrators are on the outside. So we start with our signal x of s, or whatever. Yeah, x of s. Transform. Then we're going to run this into an integrator, 1 over s. And the thing I always forget is, do the a's go on the right side or the a's go on the left side? If I remember correctly, the b's will be here and the a's will be here. The negative a's will be here. Let's check that. I wanted to make sure I'm not saying the wrong thing.
You can do like either one.
I think there probably is some interchange, but there is like a standard way of doing it called direct form 1. I think we should just keep with whatever he does. You're right. Probably practically, it's probably no different. Yeah. Isn't A0 already 1 in this case? A0 is already 1. Yeah, I didn't have to do anything. I'm just mentioning it just because I want to make sure that people know that you have to do that. So, okay, so for the direct form 1, the b's go here and the negative a's go here. Great. Got a bunch of confirmation. We'll just do that. So what was B1? B0. So the gain with B0 is going to go here, right, to this part of the system. I'll just do it generally for now. So then you're going to have B1 here. Give me an adder. And then you're going to have another integrator. So how many integrators do we need? We need 2, right? Because you're integrating twice. 1 over s. And then you're going to have your B2. I'm just going to do it generally for now, and then I'll put numbers in a second. And then here, we're going to have our other part. So this is going to be another adder, right? This is going to be technically where A0 would be, but you never actually, like A0 is always 1. It has to be. Then we just do this again. So we put integrators along the outside, right? So we have one here. So this is going to go this way. Adder. And this is going to be negative A1. B1 is 0, yeah, but I'm just going to put the numbers in a second. Yeah, that's right. So then 1 over s, and then this is going to be negative A2. And you're going to add these two guys together. And that's it. That's the general form of direct form 1. That's going to look like. Now, let's put our actual numbers in, right? So this is a gain of 1. This is a gain of 0. And this is a gain of 4. So this is going to be nothing. You don't put anything there. This is going to be, so this is going to be negative 4 here, right? And this is going to be negative 3. So to simplify this a little bit, right? So let me just copy it down. This is just a gain of 1, so it's just a wire. Gain of 1 is just a wire. Gain of 0 is just a short circuit, or an open circuit, I mean. Nothing there. I don't need an adder here. And then gain of 4, like 1 over s is just the circuit element that does the integration, right? Because see, that's what we have here, 1 over s. It's 4 over s squared. So if you try to trace it, right, it's going to be 4 over s squared, because you got 2 of them, 4 over s squared. So you're multiplying by 4, and you're multiplying by 1 over s, 1 over s. Remember, in Laplace, in frequency domain, we multiply when we go through a system. So 1 over s times 1 over s times 4, that's exactly what that is. And then plus 1, which is the actual signal itself. That's what the 1 over s represents here. Is the adder on the bottom left is the adder bottom left of a's this guy, right? That's what you're saying? I'd probably not. No. Even generally, I think it's not. Yeah, that makes sense. And yeah, so I think I can just get rid of that, and then this can just go away. But I think that is the simplest form other than direct form 2. Is that what matches what I did earlier? I mean, does this match what I did earlier? Yes, it does, because that's the answer. There you go. So this is what I would say, this is my direct form 1. Yeah. How did I get these values? I mean, I kind of, there you go. That's how I got them, right? So B0, A0 is your constant term. We don't need to indicate A0. A0 has to be 1, so we don't need to indicate that, but we just get rid of it, but I'll just say it. Someone asked, do we need to indicate A0? So we don't, but I will. So B0 is just a constant term. B1 is the coefficient with the 1 integrator. B2 is the coefficient with the 2 integrators. A1 is the coefficient with the 1 integrator. A2 is the coefficient with the 2 integrator. So yeah, so that's the general form, and this is the specific. A0, we don't touch A0. A0 is going to be 1, and that's exactly what we have here. Yeah, and the question we also need to do, yeah, so, I mean, that I would say I would do that at this step. To be honest, yeah, I would do that at this step. I would do that at this step. Because it says do not count any scalar gains stages with unity or 0 gain factors. That's basically all I've done. I've gotten rid of those and like an adder. But I think that counts as do not count those. It's a little unclear, right? It's a little unclear. I don't know if I should start counting here or if I start counting here, but what I would count here. Yeah. So well, I mean, you know, number of integrators. What is it called? Adders. 3. And what was the other one? Amplifiers. Also 3. Yeah, I agree. It's my finalized direct form 1, which doesn't have which has what they wanted us to not count here. So okay, let's do direct form 2. So direct form 2, I'm gonna look at this again, right? I just need this. H of S. Direct form 2. So this time we're gonna put all our integrators down the middle, right? So how many integrators do we need? We need to go to the second integral, right? So I'm just going to start with that. I'm going to start by drawing my 2 integrators. 1 over S. 1 over S. Okay. Now we need to okay, well, you have our input X, and we need to have our output Y. So now the A values go here, but I think they're also negative, and the B values go here. I don't know if that's right. I'm gonna check that, but that's the only thing I forget always here is which way goes what. So direct, what happened? Direct form 2. The A values are, yeah, that's right. The A value, yeah, that matches what I did before. So I think that's correct. So this will always just connect like that, always, because A0 is always going to be 1. You just leave it like we just connect the wire right there. That's all. Then here it's going to be amplifier this way with a gain of A1. I'll put the numbers in a second, but just for now, that's what that is. Let me try to draw a little neatly, at least slightly. Negative A1. Negative. Then here we have just another amplifier, right? Which is negative A2. And that's going to be connecting like that. Yeah. Again, I'm doing it generally, right? So, okay, so here's our plus, and then here's our B1, because it's the B value after the first amplifier. Here's our B2, which is the, not amplifier, I mean B value after the first integrator. And then B2 is our B value after the second integrator. So that's the general direct form 2 in this kind of thing. And then what I'm going to do now is I'm just going to plug in our actual value. Oh, sorry, there's supposed to be a B0. There's a B0. But that's the general form as a B0 after no integration. Okay, so let's plug in numbers now. So B0 is 1, so that's just going to be, this is going to be a wire. B1 is 0, so there's just nothing there. Right? And B2 is 4, so we're just going to put a 4 there. A1 is 4, so it's going to be a negative 4. And A2 is 3, so it's going to be negative 3. And yeah, that would be my direct form 2. The X and Y switched? No, I don't think the X and Y are switched for direct form 2. I think someone asked me this yesterday. I think that is still correct. But let me check. I can, what can I check? I can check the end of my notes. I remember I put the pictures there. So direct form 2 has X of S and Y of S. Yeah, it's still same one. So mainly the thing to remember, like the branch, the shape is pretty, I think, pretty easy to remember, because you either, like direct form 2, you have integrators down the middle, or you have integrators down the sides, and then maybe directions. The only thing that's like really you have to like remember is like what's what, like what side goes what for A and B. So for direct form 1, it's this. That's for direct form 1, right? B and negative A. And then for the other one, it's negative A and B. So A is always negative, B is always positive, and then we deal with it just if you just flip the sides, right? So how will we memorize this? 1 and B has a little 1. The stem of the, it looks like a 1 kind of. So the 1 goes first. There you go. That's how I'll remember. I don't know if that's helpful. Given the direct 2 form, how would you go back to the equation? Yeah, I mean, it's not too hard probably. So if I look at this, I'd say, okay, well, what do we have? We have an integrator. I guess I think about what would cause me to construct this. So I have an integrator, which brings me to this, right? And I have another integrator, which brings me to this. These are my negative A values, and these are my B values. So first of all, and I have a 1 here, right? I have a 1. So first of all, I know that that H of S, the numerator, is going to consist of a 1 because of this wire, and it's going to consist of a 4 over S squared because of this wire. And then the denominator is going to consist of it's going to consist of a 1. It has to consist of a 1. Yeah, good call. So then the denominator, well, this is negative 4, but I know that when I do this, it's going to flip the sign, so it's going to be positive 4 over S, and then a positive 3 over S squared. So I'd reconstruct it like that, and then multiply everything by S squared, and you get your H of S. So that's how I would go from direct form 2 back to the equation. Okay, that is that part of the question done. There's nothing else there. Oh, I got a number. How many? But whatever. Integrators 2, adders 3 still, and then amplifiers 3 still. So most of the improvement is that we reduce the amount of integrators. So reduce the amount of paths. The rule for dividing everything is you divide by the S term with the highest power of the denominator, right? Yeah. You need to have a 1 here. You need to have a 1. No, if B0, if this was like a 2, that's fine. You just have a gain of 2. Yeah. So you don't need to have like the important thing is that A0 is always 1. That's the important. Let me just quickly like show an example. We only need a 1 in the denominator number. It doesn't need, we only need a 1 in the denominator. The numerator doesn't need a 1. Yeah, that's correct. Yeah, that's right. You want to get everything as, you don't want to have any S's, right? If we have like S3S squared plus 5S plus, see? That's, my handwriting is going to be causing us trouble. 5S plus 2. Yeah, then you just multiply by, that's fine. The 3 is fine. But if that was in the denominator, let's say you had whatever, S squared plus 2S plus 1. Let's just say that. Then you need to get rid of this 3. So what I would do is I'd just like basically factor out a 1/3, right? So how would I explain this? Like from this denominator, I'm going to factor out 3, right? So it's going to be 3 out here over 3 over 3. And then I fixed it because now it's a 1/3 factor on the top, right? So there you go. So that's fine. That's fine. Oh yeah. 1/3. Yeah, 1/3. Yeah, sorry. I meant like. Would the gain of each term be the factored out terms? Yeah, like multiplied. Each branch of the factored out terms. It would be all of them would be multiplied by a thing. A0 is 1 right here. A0 is 1. Oh, sorry, but in this, like, before I fixed it, A0 was not 1, but it was 3. But now I've gotten into an equivalent form in which it is 1 now, because it's 1 s squared. It's the a's are on the bottom and the b's are on the Okay, great. That's that. Let's take a look at part D. Part D is let x of t be that, which is the input to the system, determine y of t, the output of the system, when x of t is the input. It's nice when the questions are short, not a lot of words, easy to understand what's going on. Blanket is still too warm. I don't know. Crazy like that? No. And so basically, we know, right, that the transfer function of the system, right, the transfer function is h of s, right, which is the Laplace transform of h of t, the impulse response. We know that our output y of t, right, is going to be the input signal x of t convolved with h of t. This was chapter 2 stuff, right? So I want to find y, right? So let's just take the Laplace of both sides. It's going to be, or let's take the Laplace of both sides. It's going to be h of s equals x of s, and now it's going to be multiplication. I guess let's all solve via convolution. That absolutely. Let's all get one question done for the whole test because we have to do convolution. Makes sense. Y of s is what I meant to write here. And then this is h of s. So when you do the Laplace transform, the convolution turns into multiplication. That's the whole point. So there we go. Now we have a way of doing this. We need to find the Laplace transform of this, and we need to multiply it by h of s, and then we got to do inverse Laplace. Right? It's a little bit annoying, but we can do it. So Laplace transform of e to the negative 2t u of t. Okay. Let's open up our table. Look at table 4.1. We have e to the lambda t u of t is 1 over s minus lambda. So that means that this is going to be 1 over s plus 2. Times h of s. We already know h of s. S squared plus 4 over s plus 3. S plus 1. So now we just got some partial fractions to do. We want to get y of t. So we found y of s, and then we're gonna do inverse Laplace on this to get y of t. Now I'll do it. I don't want to waste time too much, but let's do one partial fractions together at least, just to make sure everybody knows how to do that. It doesn't take that long. To be honest, it's not even a 5-minute thing. It's a maybe 2-minute thing. It's a boring 2-minute thing, but it's 2 minutes. So we know that, okay, so I want a partial fractions. That's my partial fraction decomposition. H equals yx. H is y over x. That's true. Another way of saying that is this. Y is xs times h. This is just converting to doing the Laplace transform. So partial fractions decomposition. So that means that basically we're saying that s squared plus 4 over s plus 2, and then s plus 3, s plus 1 can be written as a over s plus 2 plus b over s plus 3 plus c over s plus 1. So working this out a little bit, s squared plus 4 equals a times s plus 3 s plus 1 plus b times s plus 2 s plus 1 plus c times s plus 3 s plus 2. Thank God there's no 5s in this question. And I'm going to do the thing where you plug in values. I'm going to plug in s equals negative. Oh no, I can't do that, can I? Oh no, I can't do that. I can plug in s equals negative 1. So then if I plug in s equals negative 1 into this equation, it's going to be negative 1 plus 4 is 5. Negative 1, this term goes away, right? Because it's going to be 0. So it's just going to be c times negative 1 plus 3 is 2. negative 1 plus 2 is 1. So c equals 5 over 2. I'm going to check that's what I got. Yeah, c is 5 over 2. Okay, we found c. Next one, I'm going to choose s is equal to negative 3. It's going to be negative 3 plus 4 is 13. Right? Or negative 3 squared plus 4, I mean, is 13. This term goes away, this term goes away this time, right? Because negative 3 plus 3 is 0. So we just get b times negative 3 plus 2 is negative 1. Negative 3 plus 1, negative 3 plus 1 is negative. So b equals 13 over 2. And then finally, for c, I'm going to choose s equals negative 2. And then s equals negative 2. So we're going to get, we can use Heaviside's method instead. What is that? What is, like with, yeah, I don't know what that is. Oh, I see. Okay, I'm unfamiliar, but maybe that's something that works. I don't know. Did he talk about that? I'm unfamiliar with this method. I think this is a pretty fast method though for finding it. He's just doing this, so I think that works. I will look that up. So plugging in s equals negative 2. Negative 2 plus 4, negative 2 squared plus 4 is 8. So 8 equals, okay, so negative 2, that term will go away, that term will go away. So it's just going to be a times negative 2 plus 3 is 1. Negative 2 plus 1 is negative 1. Negative 1. Negative 2 plus 1 is negative 1, right? Yeah. And then so a equals negative 8. That's what I got before you. So that means, finally, our h of t, or h of s, I mean, or y of s. Right, this is y of s. I didn't write that. Y of s can be written as a over s plus 2, so negative 8 over s plus 2. Then we have b over s plus 3. What was b? 13 over 2. So plus 13 over 2 over s plus, what was it? S plus 3. Plus c was 5 over 2. 5 over 2 over s plus 1. Yeah. That's right. Okay, so now I'm going to do the inverse Laplace, right? H of t, I mean. Y of t, can't say the right thing, is negative 8. This is e to the negative 2t. Well, I'm going to put a u of t on everything after. So just leave it like that for now. 13 over 2, e to the negative 3t. And 5 over 2, e to the negative t. And all of this times u of t. Because it's a unilateral Laplace dealing with causal stuff. So there we go. That is, that's a 5, by the way. Just to be clear, that's a 5. That is my y of t, output of the system. Relatively straightforward, to be honest. The next one, takes a little bit of work, sadly. So the next one, I heard saw some people talking about it. So yeah, I have an answer. I think my answer's right. Not just someone else's answer. So the next one is the same question, but this time we have x1 is this function, which is 2 plus cos t, 4 plus cos 2t, determine y1. So again, we know, like, you know, we know that y1 is going to be equal to x1 of t, convoluted, involved, not convoluted. I always say convoluted. Involved with h of t. Laplace transform, so okay, Laplace transform. Let's do that. Y1 of s equals x1 of s multiplied by h of s. But our issue is, okay, what's the Laplace transform of this now, right? We know this Laplace transform multiplied by this. What's the Laplace transform of this? Well, there isn't really a nice one for this, right? Because Laplace transform is all about causal signals, right? Which means that they have to be, we're talking about right-sided signals here for the unilateral case. This is an infinite signal. So my logic here, like, there is a formula for this, for cosine bt u of t, but there's no u of t here, right? This is an infinite signal. So basically, you can either interpret. Would that be the same thing if you just interpret it as if there's a U of t there? Not even. Yeah. So basically, I instead do the. Oh, I have the chat message. Can I scroll up a bit? I can scroll up. Okay. Basically, my logic here is, since there's no U of t's, I'm gonna do the Fourier transform instead. Because there's no U of t's, so putting a U of t on there I feel like would just be adding stuff. Maybe if you interpret it as that there's supposed to be a U of t there, maybe that's the same thing. We also can't do the Fourier transform, the Laplace transform of 2. Maybe we can by definition, but it's not on the table. But of course we can by definition, but yeah, strange. Okay, anyways, this is my logic. It doesn't have U of t, so do the Fourier transform instead, right? Because Laplace transform is about causal signal. And we know how to do the Fourier transform of pure sinusoids, right? Yeah, well, Laplace of 2 would just be 2 over s. Yeah, you're right, actually. You're right. But in this case, but even in doing that, you're kind of assuming that there's a U of t there, right? Because the inverse Laplace of 2 over s is U of t, or 2 U of t. Right? So it just seems like if there's no unit step functions, just do the Fourier transform. So doing the Fourier transform, relatively easy, right? Well, sorry. Yeah, relatively easy. I mean that like, relative to doing the Laplace transform. So let's give it a try. So then we're going to use a couple formulas from the Fourier transform table, right? Laplace supremacy. Fair. So the Laplace transform, the Fourier transform table, the first one we're going to use is number 7, which is 1. The number 1 is 2 pi delta omega. So since we have a 2 there, so right now I'm finding x1 of s. That's what I'm doing, right? x1 of s. So since there's a 2 there, it's going to be 4 pi delta omega. Okay. Cosine t, let's go back to our table. Cosine omega naught t is on the table. That's number 9. And that's going to be pi. So I'll just write it. The whole point was that I don't write it, but I don't want people to be confused. So this is going to be pi delta omega minus first, yeah, doesn't matter. Omega naught plus delta omega plus omega naught. Sorry for that. So then and then sine. Oh, there's no sine. Never mind. So that's all we need. So let's do it. So this is going to be cosine. So it's going to be pi delta omega minus omega naught plus delta omega plus omega naught. And then I need more space. So this is going to be this. Move that over. Then we have a plus. So it's going to be 4 pi, right? Because there's a 4 here. 4 pi. And then it's going to be delta omega. Oh, sorry. But omega naught is 1. So I can just put a 1 here. My bad. So 1, right? And then the omega naught is 2 here. So it's going to be minus 2 plus delta omega minus plus 2. So that's our x of omega. That is our Fourier transform. The Fourier transform, by the way, also does this, right? Like this is also true for Fourier transform. So that's fine. We're good. And how do we get h of omega? I'll talk about that in a second. How do we get h of omega? It's very easy. You just put it in, but there's a condition, right? Has to exist. But anyways, we'll talk about that in 1 second. I think because we were never given or considered the left-sided version of cosine t, we use the equation from the formula, the Laplace equation, you're saying? Like you would use the Laplace one? Yeah, possibly. I didn't do it like that. We can try it. We can try it after, see if it gives the same thing. This also works. Like this also does give it to you. And it's actually not wildly complicated. So that is, I mean, like it's kind of complicated, but that's basically it. So this is everything here. I'm going to actually multiply everything in here. I'm going to multiply the pi in to here, just so we have a bunch of terms, right? 4 pi and 4 pi and that. So great, that's our x1. Now what's h of omega? H of omega is equal to h of s evaluated at s equals j omega. But the Fourier transform has to exist. But as we saw in the first part, part A, it's Bibo stable, which means the Fourier transform does exist, which means we can do that. So that's all you do. You just, instead of having s, you just put j omega. So that's going to be j omega squared plus 4 over. Yeah, the system is causal, so the system is causal. Yeah, we auto assume u of t. Possibly. Okay, how about this? Maybe I'll get to a point here. Maybe I won't go all the way to the end, because I have the answer of all this rearranging. But anyway, so, and then maybe we'll try it with Laplace. Let's do it. But let's see. Let's just finish this part here. So this is going to be, it was s plus 3, s plus 1, right? S plus 3, s plus 1. S plus 3, s plus 1. It's going to be j omega plus 3, j omega plus 1. And so that's it. That's our h of omega. So our y of omega is going to be x1 of omega times h of omega. Now, this looks like hell to figure this out. It's actually not that bad, because remember the sampling property. When you multiply by deltas, it's like you're just putting a value in. So basically, the first term, right? You just think about like you're multiplying this by everything, by every term here. There should be no bracket. You're multiplying this by each term here. So let's start with this. All that times 4 pi delta omega. Delta omega, it's like delta omega minus 0, right? It's as if we can just use the sampling property, plug in w equals 0, omega equals 0 into here. Omega equals 0, this is just 4 over 3. 4 over 3 times 1, which is 4 over 3. So it's just 4 over 3 times 4 pi delta omega. That's the first term. Just make sure. 4 pi. 4 over 3. Yeah. 4 pi delta omega. Yeah, that's what I have. It's a little bit of a mess, but yeah, that's what I have. Then okay, that's it. Terms are going to cancel faster than you think here. So then we multiply this term times this term, right? So we're going to have a pi. Omega minus 1, that means I'm going to plug in omega equals 1 into this. So it's going to be j squared, right? J squared plus 4, so plus j squared plus 4 over j plus 3, j plus 1. Delta omega plus 1. And then for the same, that's it for that one. I mean, we can simplify it a little bit in a second, we will, but that's it for now. And then this one is the same thing, but it's going to be a plus 1 this time. Oops. Yeah, this is supposed to be a pi here, yeah. The pi plus the pi. Then it's again going to be pi, and this time I'm going to plug in -1 for j, right? So it's going to be, still this is going to be j squared plus 4 all over, and this is going to be 3 minus j, 1 minus j here. Is it w minus 1, not w plus 1? Where? Oh, here? Yeah, here. Thank you, that's right. W plus 1. Delta of w plus 1. And these last two terms actually go to 0. Because think about what's going to happen here, right? This is going to be, I'm going to plug in 2 for j, so it's going to be 2j squared, which is -4, right? 2j squared is -4, so -4 plus 4 is this, and that same thing is going to happen here. So those are just plus 0 plus 0. Plus 0 plus 0. So hopefully that makes sense, right? Because delta w minus 2, I think yeah, right? For delta, yes, that's correct. What you're saying, yes, that is correct. So yeah, so w minus 2, I plug 2 into this, it's going to go to 0. plug positive 2 into this, it's also going to go to 0. So that's a 0. And yeah, where do we go from here again? What did I do next? What was it again? I went back to time domain. Okay, so from here, I went back to time domain. Let's simplify a little bit before we do that. This is going to be 16 pi over 3 delta omega. Because we're looking for y of t, right? So we can go back to time domain now. So that's negative. This is pi is multiplying like this, right? Pi is multiplying. Yeah, it's 0 because we're plugging in w equals 2. So it's going to be j, 2j, right? 2j squared is negative 4. Negative 4 plus 4 is 0. Same thing is going to happen if you put the negative 2 in. It's being squared. So let's just simplify a little bit here. So this is delta. Negative 1 plus 4 is 3. So it's going to be 3 pi over j plus 3 j plus 1 delta omega minus 1 plus same thing is going to be 3 pi over 3 minus j 1 minus j delta omega plus 1. How did you get the second blue highlighted term? So what was it? Which one? The like for this term? For this here? This guy? This guy? Or this one? This one is in the box here. Yeah. That's here I kind of describe it, right? So that's h of omega. H of omega is you just take h of s, and then you just substitute in s as j omega. That's how you get the Fourier transform from the Laplace transform. And we can do that because we showed in this first step here, Bibo stable. We saw it's Bibo stable, so that means the Laplace transform exists. So that's everything. No problem. So now we're going to do the inverse Fourier transform. So we're going to un-Fourier transform this. So if we look at what that is, right? Basically, it's a little confusing, but so the formula is 2 pi delta omega goes to 1, right? So I need to have a 2 pi in front of everything like this. It's not too hard here. So I want a 2 pi here. So 16 pi, I can break that up into 8 times 2 pi, right? 8 times 2 pi. 3 pi is a little harder, so I still want a 2 pi here, and I'm going to have to multiply by 3 over 2. So this is still 3 pi, right? This is still 3 pi. But I'm just getting a 2 pi here because it's 2 pi delta omega, which I'm going to transform. So same thing here. It's going to be 3 over 2 times 2 pi. Just want that to be. So now we can do our transforms. Now I'll deal with the fact that I have a bunch of coefficients here. I have a bunch of blah, 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 blah. But, and I have the shift, but I can still do the transform just in the meantime. So it's going to be 8 over 3 times 1. So the inverse, so this is now y of t, by the way. This is y of t. This is y of so f, whatever, draw fancy f inverse. So inverse Laplace of this is 1, right? So I put a 1 here. Then we're going to add 3 over 2 over, I'll write like this, 3 over 2 j plus 3 j plus 1. Inverse Laplace of delta is still 1, but I have a shift. So let's think. What's our shift property? Well, we don't have to think. We have our formula sheet. So Fourier transform. If we look time shifting, we're not doing time shifting. We're doing frequency shifting. So if your frequency shifting is x of omega minus, it's x of omega minus omega naught, and you turn this into time domain, this is x of t, e to the j omega naught t. So that's what I'm going to do here. I'm going to multiply this by e to the j omega naught. What's omega naught? Omega naught is just 1. T, e to the jt. So that e to the jt comes from this. Okay, so it's going to be the same thing with the other. It's going to be negative. So with the other one, it's 3 over, so it's still 3 over 2, 3 minus j, 1 minus j, times 1, and it's going to be e to the negative jt this time, because omega naught is negative 1, so you flip the sign. And again, this e to this guy is from this guy. So hopefully that makes sense. So, I mean, to be honest, this is right, but it's actually a real number. This is actually always a real number. Because it's a little hard to like tell right off the bat here. I mean, it's like, yeah, actually, could you just do it like, can I just factor out? Oh no, that's gonna be minus. We don't want minus. Yeah. Yeah, for 5 marks there has to be a faster way. Maybe. Yeah. Laplace transform is gonna be just as long, to be honest. Like maybe not just as long. I guess there will be the sampling stuff. So how about this? For the rest of this question, yeah, we can try it. Let's try it. It will be a real number. For any value of t. So the way you would know that is you would turn e to the jt, right? E to the jt into sine t, or cosine t plus j sine t. And you turn this into cosine t minus j sine t. So just to be clear here, this is cosine negative t, but cosine negative t is equal to cosine t. And this is sine negative t, but sine negative t is the same thing as negative sine t. So you just do that. Would people like me to see me do that? I guess you can kind of decide. We can also move on to the next question. So you basically, the rest of the question is do this and then collect like terms, and you will see you'll get real numbers as your thing. I'm getting a bunch of no's. I'll post my solution. How about this? It's actually relatively cleanly written, to be honest. Yeah, actually, it's actually is written nicely enough from when I did it before. So there is my previous solution for how it is. So there's our expression, same expression we have right now, right? Turn it into sines and coses, collect like terms, and it turns out that like that term is 3 over 8, 3 over 10, and that whole thing is 3 over 5. So you get a real number. Okay, great. One question done. One question done. So we definitely don't have time to do everything. So let's scan through the test, and I wish I could make a poll. A poll would be so good right now. Does anybody know how to make a poll? Probably someone knows how to make a poll. Optimize. I wish there was just a button that says make poll. Very Googleable. It's a very Googleable question. Yeah, not sure. Okay, let's look through the test together. And then we can choose the question we want to do. Okay, I think we'll... You know what? Yeah, actually, I think you had to enable it when you first make the call. Yeah, I didn't make the call, sadly. So. Maybe. Let's look through the test. You know what? Let's make a straw poll. Straw poll. Straw poll is always easy to make. Here, let's do it. I'm getting a lot of question 2s. I think question 2 is going to be, what question? 2, 3, 4, 5, 6. Is there 6 questions? I'm kind of guessing here. Where is it?
7 questions.
7 questions. 7. What question? Multiple choice? Yeah, multiple choice. Don't select. I guess you can select, to be honest. Yeah. Okay. Great poll. Okay. How do I send the link? There's a link. All right. Make your choice. I'll vote for number 2. I don't know. The results. There's our polls. Okay, we're getting a lot of 2s. In fact, we're getting only 2s. Okay, let's do. We're getting a lot of 2s. Okay, I'm gonna do. We're so close to 50% of the whole call. Oh, I got question 3. All right, guys, I'm doing question 3. Okay, let's do question 2. Pretty unanimous. A poll was not necessary. So, yeah, democracy. It's true. So actually, let's do here, right? 32. Great. We're more than 50% of the whole people, so won the popular vote. So here's question 2. Question 2 is consider blah blah blah. It's a little weird. It's not that bad, to be honest. The question. It's just kind of weird to draw the spectra. So let's do it. So consider the periodic impulse train S of t as shown in this figure. Boom. It can be written as a Fourier series, of course. S of t is the sampling signal for this non-ideal sampler. First of all, we need to find Sn. We need to find Sn, right? Sn is the Fourier series coefficients for the periodic signal, right? So there's a few ways you can do this, right? One way you can, like, there's many ways you can do it. One way you can do this is you can find the Fourier transform of just one of these guys and then work backwards from that, which, to be honest, probably is the easiest way to do it. Or you can just do it by definition. You can just do the integral. Let's actually do it by doing the Fourier transform. I think that's not how I did it before, but I think that's better. So to find the Fourier transform, so Sn, right? Sn is just going to be 1 over t times x, or s of j omega, evaluated at omega equals n omega. This is a formula. This is a way to convert from, so if you have a periodic repeating signal, right? I guess probably my camera's covering that, so if you have a periodic repeating signal, which is what periodic means, so a repeating signal, and you can find the Fourier transform of just one of the periods, right? One of the segments, call that S of j omega. If you want to find the Fourier series coefficients of the repeating pattern, it's just 1 over the period, the repeating. So in our case, that's TS, right? So TS, what repeats every TS, and then S of j omega. But you evaluate that at n omega naught. So we got to find this, evaluate it at n omega naught. So it's gonna be j n omega naught, and then multiply by 1 over TS. So let's find the Fourier series. The Fourier transform. Our actual S of t, I'll call it S1 of t. So it's like one single period of it, right? S1 of t, just the middle period. What is it? Well, it's the rectangular function, right? It's rect. So it's going to be this. What's happening? So the gain is 1, right? And we're now compressing it, right? Well, actually, we don't know if we're compressing it, to be honest. So usually, this is how I think about it. The regular function like this goes from -1/2 to 1/2. Let's just say that TS over 8 is bigger than this. It doesn't really matter if it's bigger than this. So actually, it's going to be the same height, but it's going to be like that, right? So this is going to go to TS over 8. So I want to write this as rect T over tau, right? That's like, I want to, it's not shifted left and right. So it's going to be T over tau. So how do I figure out tau? Basically, tau, you can figure it out because 1/2 times tau is going to give you TS over 8. That's how it always works. 1/2, which is what this point is, right, is going to get multiplied by whatever the tau value is. So 1/2 is going to get multiplied. So it's going to end up at TS over 8. But I always want to figure out, I want to retroactively reverse engineer it to figure out what this is. So that means that tau, oh, probably my camera's covering. Let's see. Oh, that's not what I meant to do. Sorry. What did I mean to do? I meant to do that. Okay, yes, just barely not. Good, just barely not. So TS, this is a true statement. So that's going to imply, let me just draw a line at where's my face? Where's my face? Okay. So I know we're not to draw past. So this is going to imply to us that tau is TS over 8 times 2, which is just TS over. So yeah. That's our tau. So that means that this is rect T over TS over 4. And I know how to find the Fourier transform of this, right? So the Fourier transform of this is on our table. Fourier transform of rect T over tau is tau sinc omega tau over 2. So S1 of j omega is equal to, like I just said, tau sinc omega tau over 2. Tau was TS over 4. Sinc omega tau, TS over 4, over 2. So just put like that. So together, it's going to be TS over 4, sinc omega TS over 8. And that is our S1 of J omega. Right? So that's what I mean, S1, like just one period. And now to find Sn, well, this is just going to be 1 over TS times all this, right? So let me just like color code it a little bit here. So let me just do this in purple. And then I'm gonna put this here, right? And I'm also gonna put that in purple. No, doesn't want me to do it in purple. All right. There we go. So the TS are going to cancel, and I have to evaluate this at W equals N omega naught. So Sn is going to be 1 over 4 sinc omega N omega naught TS over 8. Yeah, is that fine? Hold on. N omega naught, but does that mean, yeah, then I have to, what is omega naught? Omega naught is the fundamental frequency of the signal, right? That's what it is, of the repeating signal. The fundamental frequency is Ws, right? So in our particular context, we're going to put Ws here, right? Ws equals W naught, right? Which they gave us here, Ws. Remember who it is. And then there is Ws is equal to 2 pi over Ts, right? Let me write that. Ws is 2 pi over Ts. So Sn is going to be 1 over 4 sinc n 2 pi, so 2 pi n over 8. Because Ws times Ts is just going to be 2 pi. It's 2 pi n over 8. So that's going to be pi n over 4. That's my final. Is that what I got? That one? Probably. Yeah. You guys got, oh, I kind of wrote it weird. I don't know why I wrote it so weird. Is that what I got before? Sorry. What did I write before? Sorry, I kind of wrote it poorly. Okay, let me answer the question. Why not just do the Fourier series? You can. That'll do. That will get you the same. How do you get the W equals N omega S? Oh, that's we just evaluate it at W equals N omega S. That's like the formula, because that's like you evaluate the Fourier transform at omega naught, 2 omega naught, 3 omega naught, -4, right? That gets you all your Fourier coefficients. Oh, yeah. Okay, I think that's right. This formula? He did it in a lecture. I can't particularly remember the lecture at this moment. He did it in a lecture, though. Probably at the end of Fourier transforms. So, yeah, probably at the end of Fourier transforms. He did. Okay, so hopefully that's fine with everybody. That's our Sn. That's one formula to do it. You can, of course, just do the actual Fourier transform. That's just the formula for converting between dn and x of omega. Read how they derive the formula Fourier transform from the Fourier series to understand where it comes. Sure, yeah, basically. If you want to derive this formula, I can show it, but it's not really relevant. I mean, it's relevant, but like, not really an engineering thing to show a proof. But yeah, the textbook does derive it. My notes also do derive it. So, is it always W naught to N W naught? Is that what you mean? W naught N? W is N omega naught. Yeah. W is N omega naught. That's what you do. Yeah. Let's keep going. So this, yeah, go ahead.
I mean, like, is always these limits, like W naught to like NWS?
Like this formula here, is that what you're saying? This limit, like that?
Yeah, these two limits, right? So it's like Ws equal W naught, like omega equal NWS, right? Is it always these two limits?
Yeah, like this is always, you replace W with N omega naught in this formula. And then the S is specific to this case. Well, I mean, this is generally the equation for W. Like this is always true, and this formula is always true. Right.
Okay, can you like scroll down a bit?
Yeah.
Okay, so you see like the third line from the bottom?
Yeah.
Yeah, this one. Is the limits always WS to W and S?
Oh yeah, sorry. That's not like an upper limit. That's just me saying. I'm just saying I'm just saying WS equals this. That's like just me saying that.
Oh, okay.
That's all I'm saying. Like WS equals W naught. In our, just for the sake of the question, just for our particular question, they just called it WS.
Oh, okay.
That looked like an upper limit. Okay, so we found A. That's my Fourier series coefficients. B, we've got to find the Fourier transform. Transforms. Oh, sorry, Fourier transform. Yeah, Fourier transform of the sample of this periodic signal. Not too hard. Basically, there's a formula for it. I could derive this formula. It's really not that complicated. I'll just show you the formula. Sure. So we know that S of t can be written as a Fourier series, right? N goes from negative infinity to infinity of Sn e to the jn omega naught t. That's it. So let's find the Fourier transform of this, right? S of j omega. So it's still going to be a sum because it's linear, right? It's linear. So n goes to infinity, negative infinity to infinity. Sn is just a constant. So e to the j n omega t n omega naught t. What is the transform of this, right? Well, the transform of this, Fourier transform, if you look at your Fourier transform table, basically, e to the j n omega naught t. There it is. Number 8. E to the j omega naught t is 2 pi delta omega minus. Let me just write it. E to the j omega naught t is whatever. Turns into 2 pi delta omega minus omega naught. That's there. So we just do that. So it's going to turn into 2 pi delta w, and it doesn't matter. I'll take, so if it's a minus, technically it should be a plus, and omega naught. Or sorry, no, this is a plus. So this is a minus here. Minus and omega. And that's the formula that he wrote on his lecture slide. This is the formula he wrote on. So you just start with the Fourier series, and you just do the Fourier transform of it. And the thing is that this will turn into that. It will turn into 2 pi this. So you just do that, basically. So 2 pi can come out. Is there 1 over t that I'm missing somehow? No. I think that's fine. Think of something else. So 2 pi can come out to the front. This is just another sum of impulses, right? N goes from negative infinity to infinity of, well, Sn. What did we say Sn was? Well, it was 1 over 4, so I'm going to put the 1 over 4 here. Sinc pi n over 4 delta w minus n omega naught. So this is going to be pi over 2, right? Pi over 2. And this is a negative infinity. And just to, like, gut check, make sure this makes sense. Remember, the Fourier series is saying that we can write the signal as a bunch of sinusoids. These are our sinusoids. So it makes sense that the Fourier transform is just a bunch of impulses, right? Because a cosine is just 2 impulses. A sine is also just 2 impulses. So you can just, the Fourier transform of a sum of a bunch of sinusoids is just going to be a bunch of impulses. That's what we have here. Infinitely many. Well, presumably, potentially infinitely many. Yeah, it is infinitely many. Yeah, that's our Fourier transform. So that's our Fourier transform. S of j or omega. That is our Fourier transform. How would you visualize this? It's just a bunch of impulses again. But what are they separated by, right? So this is our axis here, right? They're just separated by omega naught. Sorry, and what's omega naught? Omega naught is omega s for us, right? Omega naught's omega s. Just for the context of the question, they just called it omega s here. right? So yeah, what's it separated by? Well, we have an impulse at 0. We have an impulse at omega s. Omega s. We have an impulse at 2 omega s, right? But I'm ignoring the sine stuff, the sync stuff. What is that doing? Well, it's just an amplitude, right? It's just affecting the amplitude. So yeah, sure, these might not all be pointing up, right? And they're not all the same size. But there's just impulses there. That's what the thought process. They're just a bunch of impulses scaled by pi over 2 sync pi n over 4. But frequency domain, they are just a bunch of impulses that are shifted and scaled. This is the omega. So with that in mind, the next two questions are not too bad, like next two parts of the question. In part A, didn't we already find the Fourier transform? We found the Fourier transform of just one single rect like that, one single thing. But we want the Fourier transform of the whole S of t. So what I did, I found the Fourier transform of S1, which is what I'm just calling just one single little bit. Do you not need to evaluate summation? It's an infinite summation. You can't evaluate it. This is it. This is what it is. There's nothing to evaluate, really. It's a sum of infinitely many impulses. Maybe there's something to do with the sign, but definitely it's. So now to do part C, which is definitely going to use this, right? So let x of t be that, whatever. X of t is this, sync, whatever, some arbitrary signal. Sync squared omega s t over 8. Be the input into the sampler. Determine the spectrum of the sampled waveform, blah, blah, blah. X of s, which is the Fourier transform of xs. Plot the Fourier transform. So the magnitude, right? Magnitude is what they mean. For omega between negative 2.5 and 2.5 omega. So what's our goal? Our goal is to find xs, right? xs, well, yeah, so xs in time domain is equal to x of t times s of t. X of t that's x of t. S of t, that's s of t, which we have like. So xs, which is the thing we're trying to plot of j omega, is going to be x of j omega convolved with s of j omega. Convolution is generally hard, but convolving with a bunch of impulses, which is what we're doing, is not very hard. You just move the transform, you move the frequency spectrum, right, of x of j omega to all the impulses. That's all that's doing. So let's just quickly find x of j omega. It's just a table thing, to be honest. Be able to use the table. So let me show you how I do it. X of t. I should put a sticky note on my screen, like where the camera is, because I'm always covering my face. I don't have a sticky note next to me, obviously, right now. I don't. Not here. So whatever. I'll just have that open so I can see. The camera's always crooked. It's always falling. Oh, isn't there a pi over 2? Oh, maybe there's a, yeah, maybe there's a 1 over 2 pi. Yeah, I think you're right. I think there is a 1 over 2 pi. Fourier transform, multiplication turns into 1 over 2 pi. You're right. I did forget about it. There's a 1 over 2. So now we want to find the Fourier transform of x of t. So x of t we already saw is, well, I'm just going to rewrite it. So it's going to be sync squared omega s over 8t. That's it. So looking at our table, Fourier transform of sync squared. What do we have? The Fourier transform of sync squared is w. So w over pi sync w t turns into a rect function omega over 2w. Okay, so it's kind of a lot happening here. Got to have a lot of numbers. Basically, You gotta figure out what is W to us. So the way I like to do this is I like to say, okay, let's. What? Don't we need the triangle transform? What number is that? It turns into a triangle, sinc squared. Oh yeah, so did I read the wrong one? Yeah. I read the wrong one. I in fact read the wrong one. 2 pi sinc squared is what we're trying to do. WT over 2 and this is triangle W over 2. So, let me just confirm that. W over 2 pi sinc squared WT over 2 triangle omega over 2W. Okay, that seems right. So the formula sheet has 1 over 2 pi j, does it? I don't think so. 1 over 2 pi j. I don't see 1 over 2 pi. Well, maybe that's the plot. Yeah. I don't even see it, to be honest. Sync. Okay, whatever. Anyways, so let's identify how we're gonna do this. The way I like to do it is I like to say, okay, looking at my thing here, WS over 2 is equal to W over 2, right? That's true for matching statements here. Okay, so I'm gonna just write that. So WS over, sorry, I said the wrong thing. WS over 8, this here is equal to our W over 2. There you go. The thing, multiplying the T. The WS over 8 is equal to W over 2. So I can solve for W here, right? W, so 2 over 2 WS over 8 is going to be W. So that's WS over 4. Great. So now what I need, right? I know that's W. I know that's WS, right? You know what? This is going to take more space than I realized, so it's going to do a little bit of this. A bit of this. That there. There. That there. Okay. So in the front of this sync, OneNote is annoying. Come on. Let me erase. No. No. Doesn't want me to erase anymore. Let's restart OneNote. There you go. Okay. Sorry about that. So x of t is sync squared omega s over 8 da da da. I want W over 2 pi in the front there. What's W over 2 pi? W over 2 pi is going to be omega s over 4 over 2 pi, right? Which is omega s over 8 pi. So I want omega s over 8 pi here. Omega s over 8 pi. But I can't just multiply by omega s over 8 pi. That's just changing the function. So I got to also multiply by 8 pi over omega s. Because this is just 1 here. The whole point of this is that this will now transform x of j omega into 8 pi over omega s. That's the little coefficient we have in the front. Triangle w over, or omega over 2w. What was w? Omega s over 4. It's going to be omega s over 2, right? Because 2 times that is omega s over 2. It's pretty complicated. This step is like confusing. But as long as you just, this is what I usually do. I just match those coefficients, solve for w from there. What should w be for us? Capital W. And then make that the number in the front here. But you can't just put that there. So you also have to multiply by the inverse of it. So that you're just multiplying by 1, really. So then, there you go. That's your x of j omega. The thing to notice here, basically, is that this is a triangle. Doesn't really, the amplitude doesn't really matter. Right? This is a triangle. Well, I guess like this, really. So the normal triangle function goes from -1/2 to 1/2, but we're going to multiply that by omega s over 2. So it's going to end up at 1/2 times omega s over 2. It's always going to multiply by this k value. That's what the horizontal stretch looks like. It's going to be omega s over 4. And this is just going to be negative omega s over. So not equals, but turns into. Let me be clear. This is going to be negative omega s over 4. That's what it's going to become over here. So this is our actual triangle. I don't know. That is our actual x of j omega. It has a width of from here to here, from negative omega s over 4 to omega s over 4. Okay. So great. Now we can convolve. So this is what we're trying to do, right? We're trying to understand this a little bit, right? So first of all, 1 over 2 pi. Come on. So 1 over 2 pi. X of j omega. We just found that, right? That's x of j omega. Convolved with s of j omega. S of j omega, we found that here. It looks scary. It's just a bunch of impulses. Right? It's just a bunch of impulses. So that's what we want to plot, basically. Right? That's what we want to plot. So let's simplify a little bit. There's a little bit of simplification we can do, right? So that's a convolution rule. I can just take this out, can't I? Yeah, I can just take this out of the whole thing. So this is going to be, can I just do that? Can I just rewrite this as 1 over 2 pi times 8 pi over omega s times pi over 2 times triangle omega over omega s over 2 involved with this? I think I can do that. To be honest, it doesn't really matter because we're not gonna graph this perfectly, right? But we can try our best, right? So the pi and the pi will cancel, and the 2 2's will cancel, so that becomes a 4, or that becomes a 2 on top. So it's going to be 2 pi over omega s times all that. Convolution is linear. That makes sense. So I think we can do that. Great. So like now we got to plot this, right? We got to plot this for omega s, or omega, absolute value of omega less than 2.5 omega s. That's what it told us. Less than 2.5 omega. So that means plot this like this. This. And okay, so this is 0. Let's just say this is omega s. Let me swear it's 1, 2, 3, 4, 5. 5. 1, 2, 3, 4, 5. 2 omega s. And then so 2.5 would be, right? This is 2.5 omega s. And then this would be negative omega s. Hard to count squares. 1, 2, 3, 4, 5. Yeah, there you go. Negative 2 omega s. And then this would be negative 2.5 omega s. So all that's really happening, right, is let's do each thing in different colors here, right? So this is our purple. So in purple, we're just going to have a bunch of impulses. But they're going to be scaled, all right? They're going to be scaled to look like a sinc function. So I don't know. Maybe they look something like, I don't know. They look something like this. They could be negative too. I don't know, right? But we just at least have a bunch of impulses here. And then the triangles are just going to appear there, scaled by whatever scaling factor is there, and scaled by this too. Okay. So it's 1 over omega s. So as, well, actually, no, that's, never mind. I was going to say something, but that would be incorrect. So never mind. Okay, so how do we sketch this? The thing we're relying on are these, like, the size of these arrows, right? So you could just try to plug it in, to be honest, right? So this would be for n equals 0, right? This would be for this is n equals 0. N equals 0, this is sinc 0. Sinc 0 is 1. So it's just a height here. It's just the height here of 2 pi over omega s, right? Because it's 1, and then the height is 2 pi over omega. This is the height of 1. Oh, we're not even considering this yet. So it's just this. All right, I guess that is the impulses. The triangle will have a height of this. That's the kind of a better way of saying it. The triangle will have a height of it. So upon this, we're going to build the triangle because it's a triangle. So upon this, we're going to build the triangle. And as I said before, right, what's the width of that triangle? It goes WS over 4, omega s over 4 in either direction. So this is going to be omega s over 4, and this is going to be negative omega s over 4. So there's our first one. That's for n equals 0. That's for the n equals 0 term. And I just found the amplitude of this, multiplied with the amplitude of this, and that's going to be our triangle right there. Let's try for n equals 1, right? For n equals 1, it's sinc pi over 4. We're not going to get it exactly, right? So, I don't know, what's sinc pi over 4? Sine pi over 4. Pi over 4. I mean, 0.9. I mean, that's not, my calculator's not giving me an exact value here. So this is where I feel like it'll kind of break down a little bit, right? Oh, sorry, it's also 0.4. It's 0.4 times 2 pi over omega s. We don't even know what omega s is, to be honest, right? So the best we can do is we know this is going to be, at least we know this is going to be a positive number. So we know it's going to be facing up. 0.9 is going to be a little smaller than what it was before, right? Because this was, for n equals 0, it was a 1. So it's still going to be facing up, but it's going to be a little smaller. The triangle will have a height of 2 pi omega s times sinc pi over 4. That is the height. A little overkill, writing that, but that will be the height of this triangle. Because the amplitude comes from this, and it comes from this. We don't know omega s, we can't write a specific number. This is also some decimal, so I'm not going to approximate it, like why approximate it? Leave it like that. And then that's it. That's that height. And the negative one will be the same, right? Because, or no, the negative one won't be the same. Sorry. The negative one will be the negative of this. Is that right? Sinc? No, sine it's symmetrical. Sinc is symmetrical. Yes, sinc is symmetrical. So if I put negative, if I put negative, it would be something. So this is symmetrical. So this is also going to be the same height. This is also going to be the same height. But it's going to be a triangle here, right? Oh, and sorry, I forgot to put the bottom bound. So the bottom bounds, this is going to be WS minus WS over 4, right? Because it goes WS over 4 in either direction. So it's WS minus WS over 4. And this is WS omega S plus omega S over 4. That's this. And this is going to be negative omega S plus omega S over 4. And this is going to be negative omega S minus omega S over 4. Right there. And then we got one more to do, basically, right? We got this guy to do. So now when n equals 2, it's pi over 2 instead, right? Pi over 2, sinc pi over 2, is also a positive number, right? So I'm setting n equal to 2 now for these two guys. And so basically, with n equal to 2, it's pi over 2 here, right? And it's 0.63. So it's still positive. It's still smaller. So it's still just going to be a little triangle. It's just going to be something like that, right? Where the height, once again, for both of these, the height, once again, is like this. And this is, so it's 2 pi over omega s sinc pi over 2. Sorry, this is also the same thing. 2 pi over omega s sinc pi over 4 for this one. And this is 2 pi over omega s sinc pi over 2. And the bottom bounds here, right? What's the bottom here? Well, this one this is going to be, let's do this one first. So this is 2 omega s plus omega s over 4. You can simplify that, but no need. 2 omega s minus omega s over 4. This is negative 2 omega s plus omega s over 4. And this is negative 2 omega s minus omega s over 4. The n? No, but are you okay? Okay. Why is ws over 4? Why is it ws over 4, not ws over 2? Because the width here is ws over 4. That's the width, like the width of the triangle goes from 0 to ws over 4, negative ws over 4. Right? Because our stretch is ws over 2, so you the original triangle goes from a half to negative a half. So now you multiply that by ws over 2. So it's going to be ws over 4, negative ws over 4. Okay, that's my answer. That's my answer. Doesn't triangle to 1? Height of 1, but not a width. Like it has a width of 1, which means negative a half to a half. It has a width of. It says in the formula sheet too. First page of the formula sheet, it says, yeah, when t is between negative a half and a half. You don't like it? What do you not like? This question? All of it? Fair. I mean, this is rough because, like, we've been going for an hour and 45 minutes, and we've done like one question. Like one question. We didn't finish this question. We did finish this. And then we've pretty much finished this question. The next one from this is the exact same process, but this time all that's changed, this guy, all that's changed with this one is that you have, yeah, just try at home. That's true. That's a good one. All that's different here is that your x of t has changed. So it's not gonna be triangles anymore. It's gonna be something else. But it doesn't really matter, right? It doesn't really matter. It's gonna be something else. The process is the same here. Figure out the amplitudes, figure out the distances. Maybe I won't do that. I can upload my solution to the exam. It's pretty messy. Like, I don't do it cleanly when I'm just doing it by myself. But I can put it. Okay, so that's that. Let's try something else. What's the last bit here? Yeah. We attempt to recover x of t from its sampled version xs by low-pass filtering. Consider an ideal low-pass filter with the impulse response that impulse response h of t in time domain with which is a sinc function will be a rect function, right? Which is gonna be like a low-pass filter in frequency domain. So y of t is the output of the low-pass filter when xs is discussed in part ? So we can't really answer the question because we don't know what that means. Like which part it would be different for different parts. But let's assume it was part D. For part D, sure, the low-pass filter is fine, right? This low-pass filter would be able to just take that, right? The other one, if you do the other part, you're gonna see that it's a bunch of impulses, right? Because the x of t is it's a cosine function, so it's just two impulses, and you won't be able to use a low-pass filter to get it out because you're not sampling fast enough. Basically, you're not sampling because the frequency of this is 3 omega s over 4, and you're sampling at omega s, which is not twice, right? So yeah, you're gonna have aliasing. So that's it. And to plot it, you just plot the middle, right? Well, maybe adjust the amplitude with this, but that's it. And then determine y of t and explain the result. You could do the inverse Fourier transform of this if you wanted to, if you really wanted to, but the inverse, what's it going to be? I mean, it's just going to be x of t, right? That's all it's going to be. Yeah, you got to transfer h of t into Fourier transform of it. You got to do the Fourier transform. That's right. There's not really much, there's a little bit of writing, but there's not that much to these last two questions. You can do the inverse Fourier transform, but also y of t is just going to be x of t. Well, it's going to be x of t for this one. It's not going to be x of t for this one if you if that's what they wanted you to do, it's going to be something a little more, right? Because it's going to be taking a couple more impulses. So maybe that's what they expect. I don't know. They did put question marks here, so I don't know. Anyways, let's try another one. So any should I go to the poll again? What's the next question 3? Question got 1 vote. Okay. Looks like we got a question 3 lover here. So let's think we'll do question 3. So what is it? Okay, we got two question 3 lovers. So looks like we're set in stone now. So question 3 is this. Yeah, question 3 is a little bit of an annoying one. I think they meant to write it differently. I think they meant to do sync pi t over 2. Because if you do it like this, easier. Things simplify nicely. If you do it like this, it's also possible. It's just much harder to draw at the end. It's hard to like figure out what you're supposed to be plotting. So I have a feeling they meant this. I can do both because they're not that much different. I'm gonna do this one just because it's possible to do it. The other one's possible too, but easier to do it like this. Obviously on the test itself, you gotta just do what it says here. But just because I've done both, like I did it like this, I did like this, things simplify nicely like this. So I think that's what they meant to do. That's what it was meant to be. So there's h of t. So, okay, figure, whatever, shows the block diagram representing the composite system S that is composed of 3 subsystems. The label of each subsystem shows its respective unit impulse response. Determine and plot the magnitude and phase spectra of the composite system S. So, first of all, let's just write down X. So, X of j omega, right, is equal to, that's not what I meant, y of j omega is equal to h total of j omega times x of j omega. What is that h total? Well, the h total is, there's 2 paths, right? So it's going to be h of j omega plus Fourier transform of that. So I don't know, Fourier transform of delta t minus 1 times h of j omega. That is your total, right? And we got to find out, okay, so what's the Fourier transform of this? The Fourier transform of this is 1, but there's a shift, right? So the shift, what is it? What did I get before? See what I wrote before here. Yeah, okay. Fourier transform of that is, so delta, the Fourier transform of delta is 1, but we have a shift. So Fourier transform, if you have a time shift, it's e to the negative j omega t naught. That's what you multiply by, right? So it's going to be, I'm going to factor out of h of j omega. So h of j omega times 1 plus e to the negative j omega times x of j omega. So what happened here? This, just do this. This turned into this. And I just factored out of h of j omega. Factored out of h of j omega. Hopefully that makes sense. Any questions? Feel free to let me know. Now, what are we doing again? We're finding y of j omega. That's the point. No, sorry. Oh, sorry, yeah. We only care about this. Sorry, I don't know why I'm doing it like this. We only care about that. That's all we care about. We only care about the total, ht of j omega. We don't know anything about the input or anything. Right? Come on. There we go. H total of j omega. So great. I mean, we've made some progress here, but now let's find h of j omega, right? H of j omega. We know h of t is, what was it again? It was sinc pi. So I'm going to call it sinc pi t over 2. Right? Sinc pi t over 2. So then here, isn't the convolution of yeah, that's true. Isn't the convolution of h of t delta t minus 1 capital H t minus 1? Or no, h of t, not capital H, which is times, yeah, that's right. But it's the Fourier transform of it, right? So we're gonna convolve, yeah, we're convolving in time domain. Yeah, which should be this. Should just be another way to get this. Because then you're gonna move it. Okay. So sinc, I'm gonna get h of j omega. Again, same way as before, right? So we have on our formula sheet, we have something for sinc. So the formula we have is, if I can copy it right, sinc pi w over pi sinc wt turns into rect omega over 2w. So in our case, right, what's what? Pi over 2 is our w, right? So I want w over 2, right? So let me just write, w is pi over 2. That means w over 2 is pi over 4. So I want a pi over 4 in the front here. But I can't just put a pi over 4 in the front. I got to also multiply by 4 over pi. So now I can just do that. So this will transform. This will turn into 4 over pi times, like what we just said, rect omega over 2w. What was w? W was pi over 2. So it's going to be 2 times pi over 2, which is just pi. So that's our Fourier transform. So finally, h total of j omega is 4 over pi rect w over pi, or omega over pi, times 1 plus e to the negative j omega. So that is our transfer function. Now that we found this, right, what we can do is plot it. That's what the question is asking for. Right? It says determine and plot the magnitude and phase spectra. So the way to do this basically is figure out what's your complex number, what's your real part, and what's your imaginary part to find the maze and to find the phase and the magnitude. So the way I did this, let's see what it was again. Yeah. Oh, that's not the same answer I got. What? 1/2. Oh, yeah, okay. So the way I did this is you want to break this into a complex number with a real part and an imaginary part. So it's going to be 4 over pi rect w over pi. Yeah, I'll leave it like that. So 1 plus, and this is going to be cosine negative omega, but cosine negative omega is just cosine omega, plus j sine negative omega, but sine negative omega is just negative sine omega. So finally, we can figure out all of our things here, right? So this is going to be 4 over pi. I'm going to multiply that in. So rect w omega over pi plus 4 over pi rect omega over pi cosine w minus minus j and then 4 over pi rect omega over pi sine omega. So what's our real part? What's our complex part? Well, to find the magnitude, right? First of all, remember that this rect function, what this basically does, this rect function is 1, right, is equal to 1 between two values. So the magnitude, right, can be thought of as this, right? The magnitude of h of j omega. It depends on if we're in that bound or not. So let me just quickly draw rect omega over pi is going to look like this, right? It's a rectangle. From where to where? Well, it used to be from 1/2 to -1/2, but I'm going to multiply that by pi now. So it's going to be from pi over 2 to -pi over 2. So the magnitude, if we're in this range, if we're from, if omega is between -pi over 2 and pi over 2, then all of these are just ones, right? This is just a 1, this is just a 1, this is just a 1. So the magnitude is just, well, how about this? We'll write it like this. Just the actual value of the function is 4 over pi plus 4 over pi cosine omega minus 4j over pi sine omega, and 0 otherwise. Because every term has a rect, right? So if you're outside of that range, it's just going to go 0. So everything's going to be 0 outside of that. So in this range, we just have this. Does this match what I had before? Yeah. So to find the magnitude now, the magnitude also is going to match this, right? Kind of like 514, right? We have this in some range and 0 otherwise. That's what the rectangle function does, right? So now to find the magnitude, well, I only really care about what's in the section. It's magnitude 0 otherwise. So in this section, the magnitude is going to be the square root of the real component squared plus the imaginary component squared. So what is that? So the real component is 4 over pi plus 4 over pi cosine omega. And the imaginary component is -4j over pi sine omega. So you're like, we're expected to plot this for values of omega? Yeah, but it's not too bad. It's not too bad. So the first thing looks a little bit bad, but it's going to be 4 squared over pi squared plus 8 over pi squared. No, sorry, 8 over, no, not 8. 4 times 4 times 2. 4 times 4 is 60, 32 over pi squared cosine omega. Plus, I'm just foiling this. I'm just foiling this here. This is going to be 4 squared over pi squared cosine squared omega. And then squaring this is not too bad, right? Because it's going to be plus 4 squared j squared over pi sine squared. Sine squared. Oh, actually, hold on. This is not going to work out how I expected it to be. Damn. So what I'm going for is cosine squared plus sine squared, right? That's what I'm going for. Cosine squared plus sine squared equals 1. But I'm going to get a negative here, which is fine. Okay, someone posted a solution to this. Let me just try to, oops, let me close that. Let me try to find that quickly. Got a bunch of things. Someone posted a solution to this before. It's fine. I'll find it. There you go. Oh, yeah. Of course, you're supposed to leave the J out. Yeah. There you go. That'll fix it. Yeah. You're definitely supposed to leave the J out. I don't know why I put the J there. So, yeah. Okay, never mind. No problems then. Great. So, thank you. That is correct. So now, finally, this will work out how we want it to work out, right? Because it's going to be 4 squared over pi squared plus 32 over pi squared cosine omega, right? And then I'm going to factor out 4 squared over pi squared, and then it's just going to be cosine squared omega plus sine squared omega. This is just 1. So this is just going to be square root of 4 squared over pi squared plus 32 over pi squared cosine omega plus 4 squared over pi squared. So this is 32, right? This is 32, this is 32. So I can factor out 32 over
16,
5.
16.
But it's times, oh, sorry. You're right. This is 16, this is 16, and then together they make 32. That's what I meant to say.
Yeah.
Thank you. So together they make 32 over pi squared plus 32 over pi squared cosine omega. I can take that out, so it's going to be root 32 over pi root 1 plus cosine omega. Oh, that's actually not, hold on, that's what's simplified further. This is what it simplified for the other one too. Oh boy. Let's see what the solution says. The solution says, yeah, same thing. So somehow this should simplify further. Two pi. Somehow this should simplify to 2 pi cos omega over 2. So you can use some identity here. I know that much. You can use some identity here. Each one. Yeah. Did I lose track of where I was for a second here? Where did the solutions diverge? Let's see. Where did that happen? So sync. So here they said it was, the solution says it's 4. Wait, here. 4 over pi. Oh no, it's already not a 4 over pi. There you go. That's the issue. Maybe this shouldn't be a 4 over pi. Let's see why. Weird. They got 2 pi over 2. Yeah. Okay. So there might be an issue here. It's just a lot of algebra. That's the thing. The process is fine. So the process, just to remind you, right, is we want to find h of j omega. We want to write it as like a, right, plus j b, right? We have this. And then to find the magnitude of h of j omega, right, we just find the square root of a squared plus b squared, leaving out the j. And to find the phase of h of j omega, right, we want to do tan inverse of b over a. Right? That's what we're going to do. And you can plot these. Ideally, when they do this, they're nice about it. So like this will simplify to something nice. This will simplify. Maybe this will be tan something here, right? This might end up being tan something. So if this is tan inverse of tan will just simplify to something. So if they're nice about it, we'll do that. Okay, I have to look through this. I have to look through this again. But basically that's the whole thing, is you do that and then you simplify and then you try to plot that with respect to omega. You can just choose points and plot it, or if it's something simple that you know how to plot, you can just do that. So I'll look through this after and see if there's any mistake here. I mean, almost certainly is. What is the correct number instead of 4 over pi? So the solution that I see, I don't know if that solution is right, the solution that I see. But the solution that I see has this written, but the only difference is it's just pi. It's just pi. It's not 4 over pi. So that they're multiplied by pi over 4. Yeah, I don't know. I'm not sure. Okay, I'll look through it. It'll be in the description of this video if I... Yeah, I said there was a typo, and I went with this guy, but the reason I went with this guy is because the solution does this as well. So I wanted to have a solution that matches. Also, I think it is meant to be. I think it is meant to be. So I think even with this, I think I made some minor mistake somewhere. But I think just on the Discord, in 532, just ELE 532, just scroll up a little bit. So yeah. that's that. It's 8:10. So unfortunately, that is our time. Kind of on a bad note because I can't figure this out. Yeah. Let's see. W equals pi over 2. W over pi is a half. Maybe. Let's see. Yeah, and what do I want here? I want to have W over... Oh, it's supposed to be W over pi. It's supposed to be W over pi. Not W over 2, because I want W over pi here. This is going to be pi over 2, which is a half. So I want to have a half here. So I need to multiply by 2. Kind of closer, but still not exactly it, because then I'm going to have... I'm just going to have a 2 here. So somewhere I have to multiply by a half still or something like that to match that solution. Or maybe that solution is wrong. You're right though. This is you're right though. So the W, the formula is this, right? W, so pi over 2 is W. And then we want W over pi. So W over pi would be 1 over 2. So I multiply by 1 over 2, but then I multiply by 2. Yeah, that's the thing. I don't know, to be honest. Yeah, it looks like it should be 2, but maybe they talk a lot about how they found this. And I mean, I think this makes sense. This is just a formula. So I think that's fine for now. That's I'll update this. I'll try to figure this out tonight, and then I'll update the document. So I'll put that in the description. But hopefully the you still understand what was how to do the question, right? The algebra is screwing us up here because it's messy. But how to do the question is hopefully the main takeaway from this, which is, okay, we get the impulse response, total impulse response, which was this, right? Okay, great, we got that, or that's what it was here, right? And now we want to plot it, so we have to write it kind of in this form, right? We have to write in this form. And the trick here was that we just recognize what's happening in this range, because the rect functions become 1 or 0, and that's outside the range. And then from there, you can just calculate these two expressions, right? Calculate this and calculate this, and hopefully they simplify to something nice that you can just plot on a curve. So I'll update this. I'm out of time, sadly. So, but I can update. I can send my solutions to the rest of them. Yeah, I can send my solutions to the rest of them. Anything that's messy or doesn't make sense, then feel free to let me know. But otherwise, that's all for today, guys. I'm here for a few more minutes to finish up if there's any quick questions. Otherwise, I hope you guys have a good night. Good luck on the test. Good luck on... Do we have a test before? No, this is the first test we have for other people. Or good luck on 531 tomorrow if you have that. Good luck on 501 on Sunday. I may do a live stream for that, but not with Muse. It will be posted on my YouTube channel. This will be posted on my YouTube channel here. Just my name. Battery levels low. Okay, guys. I will stop the recording for now.